Hello, everyone, and welcome once again to our Industrial Electronics and Force session. I'm C. Tobejani, and in today's session, we'll be looking at complex numbers. In today's example, we'll be directing it to example 2.17 of the TVET First textbook by Macmillan and Troupant publishers. What we'll be looking at today is how to calculate RLC circuit by making use of complex numbers, as you had already learned about the rules and how to convert these complex numbers, more particularly the polar form to rectangular form and the rectangular form to polar form. Now let us dive into our question. Here, we are expected to calculate the total impedance, the current, and also draw the phasor diagram of the circuit in 2.59a. The first thing that we need to do is to identify our impedances. Here, I'm able to identify that this can be named as Z1, this Z2, and this one to be Z3. Now let us write them in a numerical order or in complex order. Z1 will be equal to 7 minus J21 ohms. Now, because we have a capacitor across Z1, then we will use a negative for discharging. But because we have an inductor for Z2, we will use plus for magnifying or magnetizing. Yes, that is the term I'm looking for. We will do the convergence afterwards. We have Z2, which is 6 plus J18. And then lastly, we have Z3, which is 0 minus J12. Of course, we do not have a resistor across Z3, but we do have our capacitance. Now let us do our conversions so that we do have polar forms of all of this. This will come in handy when we are calculating, then we will know when to then use the correct notation. Remember, colleagues, always use your calculator and ensure that it is resetted so that it is in its reset mode and it's ready to use. Now let us convert to polar form, to rectangular form, pardon. Z1 will be 22.136. This is 22.136 at an angle of, you go check that, negative 71.565. Negative 71.565 ohms. We go ahead again and convert the other one to polar form, which is 6J18. We get 18.974. This is 18.974 at an angle of 71.565. 71.565. And then lastly, we convert the Z3. We don't have to convert the Z3 because it is already in a series combination. However, just so in case, we have 12 cis 90. 12 cis negative 90 degrees ohms. Like that. Perfect. So just like a normal RLC circuit, what you are going to have now here, and this circuit, if it's redrawn, we are going to have Z3 connected in series with the parallel combination of Z1 and Z2. This is what we have. So now we want to be calculating the Z parallel part, which is Z1, Z2, Z1, Z2. Now what do we have here? Z1 is given by 22.136 at an angle of negative 71.565. Z2 is given as 18.974 at an angle of 71.565 divided by 7 minus J21 plus 6 plus J18. Now, why am I using different notations here? Remember, in the laws and the rules of how to calculate complex numbers, it was identified that you can only multiply, it is easier to multiply polar forms than it is for rectangular forms, and you can only add or subtract rectangular forms than polar forms. Hence, that is the reason we have different notations here. Now, let us punch in our calculator. What we're going to do, we're going to punch in the 22 multiplied by the 18 there. So we're going to say 22.136 multiplied by 18.974. And we're going to get 420. This will be 420. And then we're going to add negative 71.565 plus 71.565. This should give us 0 degrees, right? And then now we want to work with the x and x, then y and our y. So we can see that 7 plus 6, this should give us 13. Let's just confirm that, but always 7 plus 6, that should give us 13. And then we have minus 21 plus 18. That should give us minus J3. We definitely gonna convert the bottom part to polar form because we are now going to be dividing. So we're going to convert 13 negative J3, and we're going to get 13.342. This would be 420. This is 0 divided by 13.4342. 342. Is it 342? 342 at an angle of what? At an angle of negative 12.995. Negative 12.995. Just like that. Still here, we're going to then divide 420 with that value there. When we divide 420 with that value there, 420 divided by 13.342, this should give us 31.4, let's just say 31.48. That will be 31.48 at an angle of, when we subtract this to that, it's going to be positive 12.995 degrees ohms. And yet we're still going to change that, of course, to a rectangular form because we're going to add it with our series, which is our Z3. So when we convert that to rectangular form, it's going to be 31.48, 12.995, and then we're going to get 30.674. That is 30.674 plus J 7.079. 7.079, just like that. And then therefore my ZT will be equal to ZP plus Z3. What is my ZP? 30.674 plus J7.079 plus 0 minus J12. Can you see that? Now, let us calculate that. This is going to be 30.674 plus 0. That will be 30.674. And then when I say 7.079 minus 12, that is 7.079 minus 12. And then we get negative 4.921. So that's going to be minus J 9.4. Is it a 4? Yes, 4, not a 9. It's 4.921. So that is 4.921. We can convert that to polar form so that it can be an easy readable number. That is 30.674 negative 4.921. Just like that, we get 31.066. This is 31.066 C's, or that is an angle of negative 9.114. negative 9.114 degrees ohms. That is now answering the first question, which is calculating the total impedance. The second question now we need to tackle is to calculate the current in each branch. Now, to calculate the current in each branch, we need first to calculate the total current in the circuit, right? So the total current in the circuit, let me use a different color here. We can use green, it's fine. We can use green, it's fine. So the total current in the circuit will be given by Vt divided by Zt. Vt divided by Zt, the total supply, which is 150, it is always at an angle of 0 degrees. So 150 angle of 0, Zt to be 31.066 at an angle of negative 9.114. And then we punch that in now. We punch that in. We're going to get 150 divided by 31.066. Just like that, we get 4.828. That is 4.828 at an angle of positive 9.114 degrees amperes. And then by using that, remember now, after we had calculated our ZT, or rather, after we had calculated our Z parallel, the circuit can be assumed to be in this way. We can have our Z parallel there, and then we can have our Z3 there. You see, Z parallel and Z3 are using the same current, which is what? Which is IT. So what I can do is I can simply calculate VZP, which is the voltage drop across the parallel impedance, just like that. Now, that will be 4.828 at an angle of 9.114 multiplied by ZP. Where is our ZP? There is our ZP, 31.48 at an angle of 12.995. Now, we punch that in our calculator. We have 4.828 multiplied by 31.48. We want to have such a big number, 151.985. 151.985 at an angle of, we're going to add our angles, 9.114 plus 12.995, and what we get, 22.109. That is 22.109 degrees volt. So we can now calculate the voltage across Z1 and the current across Z1 and the current across Z2, because we know that when two resistors are connected in parallel, they share the same voltage but different in current. So we're going to call that IZ1, or just simply I1, which is going to be equal to VZP over Z1. This is 151.985 at an angle of 22.109 divided by Z1, which is 22.136 negative 71.565. Still here, we punch in our calculators, 151.985 divided by 22.136. What do we get here? 6.866. This is 6.866 at an angle of, what is our angle here? It's 22.109 minus negative 71.565. Like that, we get 93.674. That is 93.674 degrees amperes. And then again, we move to I2, which is VZP over Z2. That will be 151.985 at an angle of 22.109 divided by 18.974 at an angle of 71.565. We punch in our calculator here still. 151.985 divided by 18.974. That should give us 8.010. So this is 8.010 at an angle of 22.3 minus 71.3. They should give us negative 49.456. Negative 49.456 degrees amperes. We've now calculated the current in each branch of the circuit. I hope you are following very well. This is very complex. One may say it's complicated, as the name implies, complex. So you must be able to follow each and every step carefully. Remember not to rush in when you are writing this in the exam, because you might make mistakes. You might make several mistakes. So you need to be slow. The last question, they want us to draw the phasor diagram of this. So when you draw the phasor diagram, we're going to be drawing a current phasor diagram. So I'm just going to be putting my Cartesian plane there. That will be my Cartesian plane right there. So I do have the current across Z1, which is I2, the current across Z3, the current across 1, and the current across 2, just like that. So what we'll do is we will be drawing that. But the first thing that we must identify is the bigger current, right? We can see I2 is bigger than I1, bigger than IT. Can you see that, right? So what I would do normally is I will start with the biggest. So that the problem is, if I start with the smallest, I might draw it to be a bit longer, right? I might draw it to be a bit longer. The line might be a bit longer. That would leave me with I2 without space to draw. So I will start with the biggest value and draw it there. So that is like that, right? So we're going to draw our I2 here, or I2 here. I'm going to make it a bit longer like that. That will be my I2. That will be my I2, which is 8.010 amps, acting at an angle of negative 49.456 degrees. Can you see that? Right. Then I come back and draw my I1. Then I draw my I1. Let me see if I can use a different color. There you go. My I1 is slightly above 90, like that, slightly above 90, like that. There. But see, this line cannot be equal to that line. It cannot be equal to that line. This is my I1, which is equal to 6.866 amperes, acting at an angle of 93.674 degrees. And then lastly, I draw my 4. I draw my what? I draw the 4. Let me use a let's use a pink color. No, let's use a purple color. My 4, which should be smaller than all of them. So I will draw it right here. See that? Just right there. That will be my IT, which is equal to 4.828 amps, acting at an angle of 9.114, just like that. So what I would do after is I would then connect this with dotted lines. Connect with a dotted line, just like that. So I have now completed drawing the phasor diagram. This in total in the exam may contribute about 12 marks. So you must check it out. It varies depending on what the examiner wants. Just study the laws of complex numbers very carefully. This will help you so that you know which diagram or how the calculations should take place. That's it for me today, folks. Let us meet again next time when we're doing other industrial electronics info circuitry problems.